Welcome to Math with Professor V. This is video lecture for section 2.6 in differential equations, and we're going to be studying equations of Bernoulli and Riccati. So in this section, we're going to study two classical equations that in some instances can be transformed into equations that we've already studied. The first one we're going to focus on is Bernoulli's equation, and you might have already studied this in Calc 2. So the differential equation dy dx plus p of x times y equals f of x times y to the n, where n is any real number, is called Bernoulli's equation. Now notice, if n is 0 or 1, then the equation above is linear in y, and we can solve it using the methods of the previous lesson, 2.5. If n is not 0 or 1, then things get more complicated, but it's definitely manageable. So as long as y doesn't equal 0, we can divide this entire equation through by y to the n, and then we'll obtain the following. We'll have y to the negative n, because you could think about it like we're basically dividing by y to the n. So y to the negative n dy dx plus p of x times, this is y to the first divided by y to the n, so it's y to the 1 minus n equals f of x. Okay. Then what do? We make the following substitution. We're going to let w equal y raised to the 1 minus n. And again, we only need to do this when n is not 0 or 1. Otherwise, just follow the procedure that we use when solving linear differential equations. From here, you're going to differentiate. So we're differentiating with respect to x. Notice our independent variable is x. So dw dx. Well, if I have the derivative of y to the 1 minus n, how do we differentiate? You bring the exponent down front, and then you subtract 1 from the exponent. So 1 minus n minus 1 would be negative n. And then we have to apply the chain rule. I'm going to multiply by dy dx. Very good. Now my goal is to make this equation become linear in w. So I'm looking at the first term. That's all you really need to focus on right here. I have y to the negative n dy dx. That's almost matching dw dx. I just need to add in 1 minus n. So I'm going to multiply this entire equation here by 1 minus n. And then now let's see what's going to emerge, okay? So we have here 1 minus n y to the negative n dy dx plus 1 minus n times p of x times y to the 1 minus n equals 1 minus n times f of x. Now, can I write this as a linear differential equation in w? Yes, because this first term is precisely what we have right here. That's dw dx. Can you see it? Yes, fabulous. Okay, that's dw dx plus, and then I have 1 minus n, that's fine, p of x. Instead of y to the 1 minus n, I can replace that with w. W to the first, okay, things are looking good, equals 1 minus n times f of x. And there you have it. So then now what do? You just solve this like we did all the differential equations in the previous section as a linear differential equation for w, okay? And then you just have to back sub, because w is y to the 1 minus n, right? So you're going to replace it with y to the 1 minus n, and then solve for y in your final answer. And that's it. So basically the idea is you have to remember this is the substitution to make. Here's the key thing when you're solving Bernoulli differential equations, and our goal is to just make them linear. Then you solve for w, and then you back sub and solve for y. It's not bad. It's actually quite fun if you tell yourself it is. Okay, solve the given Bernoulli equation. Here we go. So it's already pretty much in the standard form for us to identify what n is equal to. Notice my derivative is isolated, perfect, minus p of x is just 1 times y equals e to the x, and then here's what makes it Bernoulli. We have an extra y squared. Remember, the linear differential equations that we looked at in the previous section wouldn't have had this term, this y squared term. So in this case, for this equation, n is equal to 2. So we're going to make the following substitution. We're going to let w equal y to the, it's always 1 minus n. So this would be y to the negative first. Then you differentiate with respect to x. So dw dx equals negative y to the negative second, don't forget the chain rule, times dy dx. Are we good? Okay, perfect. Now what you do is you take a peek over here and you go, I want to make this match dw dx. So what's it missing? It's missing negative y to the negative second. So let me just rewrite it. I'm going to go step by step this time, and then in the next example, we can kind of skip a bit more. Okay, I'm going to multiply everybody through by negative y to the negative second because my goal is to have this first term here be dw dx. So now let's see what we got. Negative y to the negative second dy dx. This will be plus y to the negative first equals negative e to the x. Are we okay? All right, good. So now, yep, this is perfect. This is dw dx plus, okay, I don't want to write y to the negative first anymore. I want this to be linear in w. Yep, y to the negative first is w equals negative e to the x. Perfect. There we go. Now we have a linear differential equation. W is the dependent variable, x is independent. P of x is just 1. P of x is just 1. So the interval on which our solution's valid is going to be from negative infinity to infinity. And then let's go ahead and find our integrating factor. So mu of x is going to be e raised to the integral of 1 dx. So that's just going to be e to the x. Now you come through, multiply the linear differential equation in w by e to the x. Let's see what we got now. So we have dw dx e to the x plus w e to the x equals, very good, negative e to the 2x. And then let's just make sure everything's checking out okay. So this first term should be the derivative with respect to x of w times my integrating factor. Is it? Let's check. Derivative of w, dw dx, leave e to the x alone. We're doing product rule plus, leave w alone, and then derivative of e to the x is e to the x. Perfect. Perfect. Integrate with respect to x on both sides. Beautiful. Then we have w times e to the x equals negative 1/2 e to the 2x plus c. Okay, perfect. Let's isolate w first. So I'm going to divide everybody through by e to the x. So w equals negative 1/2 e to the 2x divided by e to the x is just going to be e to the x. And then let me write this as plus c e to the negative x for now. We'll see where things are going. Okay, then who was w? Go back. W, right here. W is y to the negative first, all right. So that's 1 over y. 1 over y equals negative 1/2 e to the x plus c e to the negative x. Okay, so if I want y by itself, let me just take the reciprocal of both sides. So y equals 1 over, and then I'm going to write this with c e to the negative x first so it looks nicer. In fact, it's c over e to the x, let's be real, minus 1/2 e to the x. And then this is technically not simplified because we have fractions within the denominator. So I'm going to multiply everybody by 2 e to the x, 2 e to the x, and then we're pretty much done. So y equals 2 e to the x over, this will be 2c minus e to the x, and then we can redefine c. So let's let k be 2c, just so it looks so beautiful and clean. So y equals 2 e to the x over k minus e to the x. Boom. There's your final answer. Oh me, oh my. And it's valid on the interval from negative infinity to infinity, so for all real numbers. Good? Okay, so the book does a pretty garbage job of simplifying I can't remember exactly how far they took it, but it's inappropriate. So just make sure you isolate, solve for y, and make sure you have no complex fractions in your final answer, okay? Let's look at another example, just so you guys can get the hang of things. If you feel ready, I would say pause the video, try it on your own. Before you try to identify what n is, though, make sure you get it in standard form, so isolate the derivative. It won't affect things this time, but other times it might. So just get in that habit, divide through by x first, okay? So we'll have here dy dx minus, this is going to be 1 plus x over x times y equals, and then we just have y squared. So why is this Bernoulli and not regular linear? Because we have this y squared term over here. Remember, we're only allowed a function of x on the right-hand side when we're in standard linear form. So in this case, that means n is equal to 2, whatever the exponent is on y, that's on the right-hand side. So we make the following substitution. We let w equal y to the 1 minus n, 1 minus 2, so 2 again. So y to the negative first. Then differentiate. So dw dx is negative y to the negative second times dy dx. And then you look up top and you go, okay, I want this to become dw dx. So what's it missing? It's missing negative y to the negative second. So everybody gets multiplied through by that. Okay, come down here. Let's multiply through negative y to the negative second dy dx plus, oh my goodness, if you miss a negative, it ruins everything because when the integrating factor's off, you're going to cry. Plus 1 plus x over x, and then we'll have y to the negative first equals negative 1. Are we all right? Okay, good. Now let's rewrite everything in terms of w. So this is dw dx plus 1 plus x over x, that's 1 over x plus 1, isn't it? Yes, 1 over x plus 1. And then this y to the negative first is w equals negative 1. Okay, can you identify p of x? Perfect. And please tell me an interval on which p of x is continuous, and therefore our solution will be valid. So you can't include 0 in the interval. So let's choose the interval from 0 to infinity. Okay, now mu of x is going to be e raised to the integral of p of x dx. So that's going to be e raised to the ln absolute value of x, but I'm already on 0 to infinity, so I'm just going to put x plus x. Do you know how to simplify this? Oh, good. So e raised to the ln of x times e to the x, right? Remember, e to the a plus b is e to the a times e to the b. And then this is going to be x e to the x. There's my integrating factor. So what do I do once I have the integrating factor? You come back to this step here and multiply everybody through by mu. So we will have x e to the x dw dx plus, now if I distribute an x through p of x, it's just going to become 1 plus x, and then we've got e to the x times w equals negative x e to the x. Perfect. Now the left-hand side is the derivative with respect to x of the integrating factor times w. And then here we just have negative x e to the x. I'll leave it as an exercise for you to verify that indeed it is the derivative of x e to the x and w, and then we can proceed to integrate both sides with respect to x. So on the left, that's the easy part, you just have x e to the x times w. On the right hand side, we need to do integration by parts. Let's just do the tabular method. It'll just be quick and easy. So x e to the x dx, I'm going to leave the negative out, okay? You can incorporate it if you want, totally up to you. I'm just going to do x, 1, 0, and then e to the x all the way down. Remember, we take diagonal products from left to right, and then the signs alternate. And I have a big negative in front here. So x e to the x minus e to the x, and then I'll put my plus c here. Okay, So I'm left with x e to the x times w equals negative x e to the x plus e to the x plus c. So I want to isolate w first. Let's divide by x e to the x. So w would be negative 1 plus 1 over x. You know what? Let me keep everybody together. I have a feeling I know where this is going. Negative x e to the x plus e to the x plus c over x e to the x. You want to know why I didn't split it up? Because I said I have to go back and solve for y. And who was w? W was y to the negative first. And that's 1 over y. So I have a feeling like I'm going to take a reciprocal. It's better if I just leave it as a fraction. I'm going to go close the window in a second. Sorry, the birds are being annoying. Okay, c minus x e to the x plus e to the x. Put that c in the front, right? It looks better. You don't want to start with a negative when you could be positive. So y to the negative first, that's 1 over y. Flip it. So y is x e to the x over c minus x e to the x plus e to the x. Bravo. Box that with pride. That's well done. Again, you know, I think the book, they wrote this. I know, I'm already like dying on the inside a little bit. And then they broke this up term by term. It's like, why come so far only to fumble at the last few steps? Please clean it up properly. Solve for y when possible. No point in doing math if you're not going to do it properly. Okay, let's do, how many more of these Bernoullis do I have? I got 2 more for you. The next one, n is not 2, which I thought was exciting. And then the last one has a little spicy twist, so. Okay, we've got y to the 1/2 dy dx plus y to the 3/2 equals 1 and y of 0 equals 4. Pause the video, try it on your own. I'm going to go shut the window so you don't hear the birds. Okay, so first things first, I divided everybody by y to the 1/2. So we'll have dy dx plus y to the first equals, let's write it as y to the negative 1/2. Okay. Ooh, so what's n equal to this time? N is negative 1/2. So we always let w equal y to the 1 minus n. So that's going to be y to the positive 3/2. Yay, fractions. Okay, then differentiate. So dw dx, derivative of y to the 3/2 would be 3/2. Y to the 1/2, don't forget the chain rule, times dy dx. Then you come take a peek over here. What's it missing? 3/2 y to the 1/2. Okay. So multiply everybody by 3/2. Ugh, that's the ugliest 3 I've written in my life. Okay. 3/2 y to the 1/2. Here we go. So this is going to be 3/2 y to the 1/2 dy dx plus 3/2 y to the 3/2 equals just 3/2. Lovely. Okay, from here, let's see. This is indeed dw dx plus 3/2. And then who is y to the 3/2? Well, this time that's w. Ah, perfect. It will always work that way if you did things correctly. Equals 3/2. Perfect. So now p of x is just this constant right here, 3/2. So an interval on which it's continuous where our solution is valid is going to be all real numbers. You have to check also where this is continuous, but it hasn't been posing any problems, so I haven't been talking about it, but please also check the right-hand side. Okay, so let's get our integrating factor, mu of x. It's e to the integral of just 3/2 dx. Okay, so e to the 3/2 x. Then what do? We multiply this equation here through by the integrating factor. And what do we get? We get dw dx e to the 3/2 x plus 3/2 w times e to the 3/2 x equals 3/2 e to the 3/2 x. Okay, phew. So double check the left-hand side should be the derivative with respect to x of w times the integrating factor. Is it? Yes, it is, Professor V. Oh, good. Okay, so 3/2 e to the 3/2 x is on the right-hand side. I'm already feeling good. I'm like, I can integrate that even on my worst day, right? Perfect. Did you put your integral sign and dx's on both sides? Don't be sloppy. Okay, so then we have w times e to the 3/2 x equals, okay, so when I take the antiderivative of e to the 3/2 x, I would divide by 3/2, which is same as multiplying by 2/3, which would cancel out this coefficient entirely. So then I'm just left with e to the 3/2 x plus c. Perfect. Okay, so then w by itself would be 1 plus ce to the negative 3/2 x. And then, didn't they give me an initial condition? They sure did. Okay, so let's replace w. W is y to the 3/2. Y to the 3/2 equals 1 plus ce to the negative 3/2 x. And then they told me, where was it? Here. Y of 0 equals 4. I recommend finding c now using that initial condition at this step instead of waiting till later, because what happens is you isolate y, then you solve for c, and you have to almost like duplicate the process over again. If you do it that way, you'll see why it's not fun. So, but you don't have to believe me. You could do it the other way, and then you'll believe me. Okay, so since we know y of 0 is 4, we're going to substitute in 0 for x, 4 for y. Okay, so 4 to the 3/2. You know how to do that in your head? You take the square root of 4, so whatever number this is, you take that root of 4, and then you raise it to the numerator. So this would be 2 to the 3rd, that's 8, equals 1 plus c, so c is 7. Okay, so now we have y to the 3/2 equals 1 plus 7e to the negative 3/2 x. Yeah, and the book left it like this. I mean, how disgusting. There's really only one thing you need to do, right? Raise both sides to the 2/3. Why couldn't they be bothered to do this? Heavens to Betsy. Okay, y equals 1 plus 7e to the negative 3/2 x raised to the 2/3. Now, I know I said, positive exponents when possible, but this isn't within another fraction. It's not like we have 1 over this. So I would just leave it like this. This looks great. This is lovely. Good? Okay, I thought that one was excellent practice because it had an initial condition and n was not an integer. So that's good to practice. Okay, last one, spiciest one of all. Are you ready? Okay, here we go. xy times 1 plus xy squared dy dx equals 1, and they told us y of 1 is 0. So first thing I'm going to do is try to get it in standard form, and I want to isolate my derivative dy dx. So let's divide through by everything that's in front of it. So dy dx equals 1 over xy times 1 plus xy squared. Yes? Now, how on earth am I going to get this into the form for Bernoulli, right? Like, how am I going to get this into dy dx plus p of x times y equals f of x times y to the n? Look at it. It's not happening, guys. I'm so sorry. Then you go, why is it in this section? They're lying to me. No, every now and then you got to be a little clever, and we're going to flip it. So we're stuck. So instead, we're going to take the reciprocal, basically, flip it, and see if things work out better if we treat y as the dependent variable. So dx dy would be xy times 1 plus xy squared. So then now kind of what's your goal? Not this. Your goal would be dx dy plus p of y times x equals exactly. So you would have, I don't know, q of y, g of y, x to the n. Yeah? Okay. So that's our new goal. Can we get it in this form? I think so. I mean, I wouldn't have told you to flip it if it was going nowhere. Okay, so dx dy, y equals xy plus x squared y cubed. Okay, so the term with plain old x needs to go on the left. See that? Okay, so dx dy minus xy equals x squared y cubed. Can you identify what's going on? Or are you in a tizzy? Okay, so here's x to the n. Here's x to the n. Yes, n is 2. Okay, so we're going to let w, be careful, equal x to the 1 minus 2. So that's x to the negative first. So dw dx would be negative x to the negative second times dx dy. Bravo. Then you come back right here and you go, I want that first term to be dw dx. So I need to multiply everybody by negative x to the negative second. All right, now what do we have? So negative x to the negative second, dx dy, plus that'll be x to the negative first y equals negative y cubed. Beautiful. This should be a linear differential equation in W now. So indeed, this is dw dy plus, who's x to the negative first? That's w, times y equals negative y cubed. Whew. Okay, now let's find our integrating factor. So p of y is y this time, right here. And then no restrictions from negative y cubed. So the interval on which our solution is valid is all real numbers, negative infinity to infinity. Let's get our integrating factor, mu of y, e to the integral of y dy. So it's e to the 1/2 y squared. Beautiful. What do I do with that integrating factor? I come through, I multiply everybody in the equation above by it. So e to the 1/2 y squared. You have to really focus, right? When it's dx dy from the get-go, you're like, whew, I feel so odd. Okay, e to the 1/2 y squared dw dy plus wy e to the 1/2 y squared equals negative y cubed e to the 1/2 y squared. Now this better be derivative with respect to y of w times the integrating factor. Is it? Check if the product rule holds up. It's a good spot to catch if you screwed up, you know what I mean? Let's do it. Derivative with respect to y of w is dw dy. Leave this alone. Perfect. Leave w alone, and then derivative of e to the something is e to the something, and then because of the chain rule, I got to multiply by derivative 1/2 y squared. There it is. We're so good. Okay, integrate both sides with respect to y this time. Beautiful. So then we've got w times e to the 1/2 y squared equals, ooh, how do you do this integral over here? Well, you might be thinking tabular, short, but we don't know the antiderivative of e to the 1/2 y squared. So we're going to make a substitution and then we can do tabular. Hopefully you've seen an integral like this when you were in calculus too. I'm going to break up y cubed into y squared and y. Okay, let's leave the negative there. And then you still have e to the 1/2 y squared dy. I'm going to do a u substitution. I sure am. I'm going to let u be 1/2 y squared. And then du would be y dy. Yes? Okay, very good. So y dy is right here. That's going to be du. Here's e to the u. And then you might be saying, well, what about this plain old negative y squared? Well, that's just going to be, leave the negative there, 2u, right? Because come here, 2u is y squared. Okay, so the left-hand side has now transformed into negative 2u times e to the u du. Can you see that? Okay, now integration by parts time. I prefer tabular DI method. So we'll put you know what, let me put the negative in here so I don't worry about it later. Boom. Negative 2u, negative 2, 0. And then e to the u, e to the u, e to the u. Take products on the diagonal. I go over tabular in another video. If you don't know how to do it, I'll link it in the description. Plus, minus. Okay. So we have w e to the 1/2 y squared. Don't forget that was patiently waiting for us on the left. Equals, so this is going to be negative 2u e to the u. And then this is going to be positive 2e to the u plus c. And then go back, u was 1/2 y squared. So we to the 1/2 y squared is negative 2 times 1/2 y squared. That's just going to be negative y squared e to the 1/2 y squared plus 2e to the 1/2 y squared plus c. Whew. Okay, then divide everybody through, yes, by e to the 1/2 y squared. So w equals, I'm going to just leave it. I sure am. C minus y squared e to the 1/2 y squared plus 2e to the 1/2 y squared over e to the 1/2 y squared. And then who was w? W was 1 over x, or x to the negative first. So then x by itself is just going to be the reciprocal. So x is going to be e to the 1/2 y squared over c minus y squared e to the 1/2 y squared plus 2e to the 1/2 y squared. You know, I was all ready to box it and then I forgot. They gave us an initial condition. So y of 1 is 0. So I'm going to substitute in 1 for x, 0 for y. So we'll have 1 equals e to the 0 over c minus 0 plus 2. Yes? Okay. So then multiplying through by c plus 2 equals 1. So c is negative 1. Okay, so then we're pretty much done, right? So x equals e to the 1/2 y squared over, now since c is negative, I don't want it out front. Let's put this 2e to the 1/2 y squared out front. That's our shining star. Minus y squared e to the 1/2 y squared minus 1, since c is negative, you know. Lead with your best, put your best foot forward, be positive. Or whatnot. Let's see. How's this answer looking? Do we like it? Yeah, we love it, Professor V. We couldn't have done it without you, though. Okay, good. So that's tricky when you have to flip it. And then that's why, too, we left our final answer solving for x instead of y, because when we were solving the differential equation earlier, remember, we flipped things around and we treated x as the dependent variable and differentiated with respect to y. So there we go. Okay, so those are Bernoulli differential equations. Now we're going to talk about one other kind, Riccati's equation. So the non-linear differential equation, which has the following form, dy dx equals p of x plus q of x times y plus r of x times y squared, is called Riccati's equation. Now here's the thing. You have to be given a known particular solution for the above differential equation. So someone's going to have to give you y1 and say, here's a solution. Then you're going to make the following substitution. You're going to let y equal y1 plus u. And then if you differentiate, dy dx would be dy1 dx plus du dx, right? I'm just going through differentiating term by term with respect to x. What does this do? Well, this leads us to the following, okay? So I'm going to substitute in, instead of dy dx, what I have here. So on the left-hand side, we'll have dy1 dx plus du dx equals p of x plus q of x times, instead of y, right here, I'm going to sub in y1 plus u plus r of x times, again, y1 plus u squared. Are we okay? Good. Now, what do I know? Well, y1 that was given to me is a solution of the differential equation. And what does that mean if it's a solution? That means it satisfies the equation. So if I find dy1 dx, this one here, then that will equal p of x plus q of x times y1 plus r of x times y1 squared. Okay, what does that mean for me? I'm going to come through right here and replace dy1 dx with p plus qy1 plus ry1 squared. So let's do that. So I have p of x, but I'm lazy to write the of x, okay, plus qy1 plus ry1 squared plus du dx equals p plus, let's distribute, qy1 plus qu plus, okay, let's be careful here. This is y1 squared plus 2 y1u plus u squared, and all of that gets multiplied by r, right? So we'll have ry1 squared plus 2ry1u plus ru squared. Okay, what happens? We have a cancel party. P is gone, qy1 is gone. This will happen when you're solving all of them. It's very fun. Okay, is that it? Who survived? I've got a du dx over here equals, I've got a qu, a 2ry1u, and an ru squared. You're like, I'm not excited about that. Hold on. 2ry1u plus ru squared. Allow me to rearrange it for you, okay? I'm going to leave the ru squared over there, move over the other two terms, and factor out the u. So it's du dx minus q plus 2y1r times u equals ru squared. Do you recognize what kind of differential equation this is now? Maybe? Yes, this is a Bernoulli differential equation. It's a Bernoulli DE with n equaling 2, because we have u squared always on the right-hand side, u squared. Okay, so basically here's how it works. Ricattis become Bernoullis, and Bernoullis become linear when you make the appropriate substitution. The way you know you have a Riccati, I don't have to even tell you, is because you have to be given a known solution. So that's like a dead giveaway. Even if in the directions it doesn't say solve the given Riccati equation, because I gave you one of them, that's your hint right there, okay? So then you know when you take the test, oh, this one's a Riccati. Okay, so here we go. We're only going to do 2 examples because, as you can imagine, it takes a while. So we have dy dx equals 1 minus x minus y plus xy squared, and a given solution y1 is 1. So you always make the following substitution. You're going to say, let's let y equal y1 plus u. So what was y1? y1 was 1 plus u. Then you differentiate with respect to x. So dy dx is going to equal derivative of 1 is 0, and then we'll have du dx. Good? Now the goal is rewrite the differential equation above all in terms of u's and x's. Okay, so dy dx on the left, I'm going to replace that with du dx equals 1 minus x minus, instead of y, what am I going to write? 1 plus u plus x times 1 plus u squared. Now you clean up, and a bunch of stuff should cancel, just like in the proof. Well, this is a semi-proof. At this step, this is where all this lovely cancellation is going to occur. So let's see. We'll have du dx equals 1 minus x minus 1 minus u plus x times 1 plus 2u plus u squared. And then sure enough, yep, 1 cancels. If I distribute, right, that x will cancel. I don't think much else, right? So I still have to distribute the x through to these guys. So let's see what's left over. I have du dx equals negative u plus 2xu plus xu squared. So that term's going to stay on the right-hand side. Everybody else has u to the first in it, so move it to the left, and we'll factor out that u to the first. So du dx plus u minus 2xu equals xu squared. And then boom, finally we can see this is a Bernoulli equation. So du dx plus u times 1 minus 2x equals xu squared. And then hopefully you can see, yep, okay, n is 2. It's always going to be that way with the Ricattis. N is 2. Okay, so what's the substitution that we make? Now you're thinking back to how did we deal with Bernoulli's? So we let w equal, in this case, the dependent variable is u. So we're going to let w be u raised to the 1 minus n, 1 minus 2. It's always going to be the same when you're doing Riccatti's because they always end up being Bernoulli's with n is 2. And then dw dx is going to be negative u to the negative second du dx. Okay? All right, next thing I do, I try to make this be the same as dw dx. So I got to multiply everybody through by, what is it missing? Negative u to the negative second. So let's do that. So then now we have negative u to the negative second du dx. This will be minus u to the negative first times 1 minus 2x equals negative x. So then, yep, this is dw dx minus, excuse me, w times 1 minus 2x equals negative x. Whew! Okay, so now it's linear in w. X is an independent variable. What is p of x? P of x is negative 1 minus 2x, so negative 1 plus 2x. P of x is continuous where all real numbers, and then check the right-hand side. Again, continuous on all real numbers. Don't forget to write your interval. So then let's get our integrating factor. Mu of x is going to be e raised to the integral of negative 1 plus 2x dx. So it's going to be e to the negative x plus x squared. So let's write x squared minus x. Okay, good. Good. Now what do? Now we go back to this step, multiply everybody through by the integrating factor. So what do we have? We'll have e to the x squared minus x dw dx minus w times 1 minus 2x e to the x squared minus x equals negative x e to the x squared minus x. Whew! All right, this is going to be derivative with respect to x, or it ought to be, of w times integrating factor e to the x squared minus x dx. No dx yet. I got too excited. Please forgive me. Equals negative x e to the x squared minus x. So check. Yes, it's good. So we will integrate both sides now with respect to x. So left-hand side, no problem. Okay, we'll have w times e to the x squared minus x equals, and then you're probably thinking, oh me, oh my. So if I try to u sub, if I try to let u be x squared minus x, the problem is du is going to be 2x minus 1. I don't have a minus 1. And then you try to play around with it and you get stuck. You really, truly get stuck. So unfortunately, though you might feel like you can integrate almost anything that comes your way, you can't. You cannot express this integral in terms of elementary functions. Elementary functions meaning ones that we've encountered thus far in our math career, okay? There's more advanced integration techniques that are beyond the scope of this course that we could use to evaluate it, but not necessary, not possible for you. So what do you do instead? Well, you're going to just set it up, generally speaking, and leave the integral in there. So you're going to say this is just negative. I want it to result in a function of x. So I'm going to write it as an integral from some x naught to x, then swap it out with the dummy variable t, e to the t squared minus t dt. And then you're going to have a plus c after all is said and done. Okay, so here's the idea. If you ever encounter an integral that you cannot evaluate, you want it to result in a function of x plus c, right, to get the antiderivative. So swap these out for some dummy variable. Typically we use t, and then you have to switch the limits so that you go from x naught, some initial value, to x. And this is irrelevant, like it will get absorbed anyways. So just leave it as so. Then you just proceed and your answer is going to look a little gross, okay? So w, who was w? It was 1 over u times, e to the x squared minus x equals, let's write the right-hand side as c minus integral x naught to x t e to the t squared minus t dt. And then take the reciprocal of both sides and divide by e to the x squared minus x. I think you can handle it. U equals e to the x squared minus x over c minus integral x naught to x t e to the t squared minus t dt. And then last but not least, who was u? U was 1 plus y. So to get y by itself, we're going to subtract 1 over. So we'll say y equals e to the x squared minus x over c minus integral x naught to x t e to the t squared minus t dt minus 1. You can just leave it over there like that to the side. Oh, minus 1, there you are. That's it. Oh my goodness. What a journey. What a journey. I don't think there's any others like this in the homework, but I just wanted you to see it. Because we just carry on. We can still solve for y even if we can't evaluate an integral once in a blue moon. Okay? Also, again, the back of the book does a very garbage job and it doesn't solve for y. So this is the form your answer would need to be in. Okay, I just got one more Riccati for you because as you can tell, it's like quite the process. You got to jump to Bernoulli land, then linear land. You know, it's like we're all over the place. So here we go. Last one. Almost there. So dy dx equals 2x squared plus 1 over x times y minus 2y squared. And the given solution is y1 equals x. Okay. So you just need to remember the substitution. We always let y equal y1 plus u. So in this case, that means y equals x plus u. And then differentiate. So dy dx equals derivative of x with respect to x is 1 plus du dx. Then we come back over here and we replace all the y's so that everything's in terms of x's and u's. So what do we have? Instead of dy dx, I'm going to have 1 plus du dx equals 2x squared plus 1 over x times, instead of y, what do I write? Very good. X plus u minus 2 times, again, x plus u squared. Are we good? Foil it all out, clean it up, and you'll have some canceling fun ahead of you. This is probably the most enjoyable part of the problem. 1 plus du dx equals 2x squared plus 1 plus u over x minus 2. Let's just get this show on the road. This is x squared plus 2xu plus u squared, right? Okay, so minus 2x squared minus 4xu minus 2u squared. So who's going to cancel? 1 goes bye-bye. 2x squared as well. I believe that's it, right? Okay, all the terms that have u to the first need to go on the left. So we can write this as Bernoulli momentarily. So we've got du dx. Let's factor it out too while we're at it. We can handle it. Plus u times 4x minus 1 over x equals negative 2u squared. Let me tell you, be so careful with the negatives, okay? If you miss one, it messes up everything. It will stress you out and you'll be sad. Okay, this is, no surprise, Bernoulli. N is equal to 2. So then we make another substitution. We let W equal u to the 1 minus 2, which is u to the negative first. dw dx equals negative u to the negative second times du dx. Fabulous. Then you come back here, you go, what are you missing to be dw dx? You're missing negative u to the negative second. So then we multiply everybody through by precisely that, negative u to the negative second. And then let's see what we got. So negative u to the negative second du dx minus 1 over u times 4x minus 1 over x equals just positive 2. Yes? Okay, so then this becomes dw dx minus, this is just my w, right? Yes. W times 4x minus 1 over x equals 2. Are we good? We're great. Okay, here's my p of x. Okay, I need an interval on which it's continuous. Don't forget there's a minus 2, okay? Whew. So the interval on which it's continuous would not include 0, so 0 to infinity. Let's get our integrating factor. So mu of x is going to be e to the integral. I'll write it as positive 1 over x minus 4x dx. Okay, so this is going to be e to the ln. I'm not putting absolute value of x because I already declared we're on 0 to infinity, minus 2x squared. And then again, break up the exponents. So this is e to the ln of x times e to the negative 2x squared, which is going to give me x e to the negative 2x squared. Are we good? Beautiful. Hang in there, guys. You're almost there. Multiply by the integrating factor. So by x e to the negative 2x squared. And then what do we have? So this is x e to the negative 2x squared dw dx. Okay, then we have plus x e to the negative 2x squared times, you know what I'm going to do? Yeah, I made this a plus, so I'm going to switch the order of subtraction here, guys, just so it looks better. 1 over x minus 4x times w equals 2x e to the negative 2x squared. Okay, so now check, please check that this is indeed the derivative with respect to x of the integrating factor x e to the negative 2x squared times w dx. You have to do triple product rule. No dx yet, I get too excited. And then this equals right-hand side, 2x e to the negative 2x squared. So it checks out, all is well. We can integrate both sides with respect to x. Okay, so what are we left with now? On the left-hand side, that's the relaxing part, x e to the negative 2x squared times w. And then over here, it's actually not bad. You could probably even do the u sub in your head. Let u be negative 2x squared. Du would be negative 4x dx. I have 2x, so I'm just going to pick up a negative 1/2. Oh, that was relaxing, especially after the last one that we couldn't even do, right? I hope you didn't take it personally and feel like a failure. Okay, very good. Now, let's divide everybody through by x e to the negative 2x squared. So w is going to equal negative 1 over 2x plus c over x. Actually, if I put it here, then it's positive, right? Isn't that nice? Okay, I know I'm going to want to switch back to u and flip it in that case because w is 1 over u, right? So I would love it if I had a common denominator. So let's do that. So 1 over u equals 2ce to the 2x squared minus 1 over 2x. I can let k be 2c. That way that looks cleaner. And then u would be 2x over k e to the 2x squared minus 1. Yay! And then who was u? Well, remember, u was y minus x. U was y minus x. And so we can solve for y, get it by itself. Just add the x over and don't worry about it. Do you know what I mean? So y equals 2x over ke to the 2x squared minus 1 plus x. Okay, everything's looking good. Again, the back of the book really just is not helpful. So this is where we'll leave it. Yeah, box that with immense pride. We made it. We made it, guys. I hope you enjoyed the video. I hope you found it helpful. Give it a thumbs up. I'll make it public. Usually I do members only, but I'll make this one public. I haven't uploaded in a long time. Don't forget to subscribe if you haven't already. And then if you need to review any integration techniques or other topics in differential equations, then I have full-length video lectures for the entire course up here on this playlist. You can also follow me on Instagram, TikTok, Math with Professor V. I'll be back sooner than later. Bye, guys.